Good evening, elites, good evening. I welcome you all again to NEET Elite. Hoping that you guys are doing great, having a good time. Well, people, you can let me know in the chat box if I'm audible and visible to everyone, yes. You can let me know in the chat box if I'm audible and visible to everyone. Give me some thumbs ups in the chat box so that I'll get to know whether I'm audible and visible to everyone or not. Hello Raja, hi Darshni, hi Arnav, hi Shweta, hello Farooq, hi Keshav, hi Sahifa, hello Tahir, hi Sania. Sania, I couldn't take the session in the morning. Okay, so that session will be on Monday now. Perfect. All right, guys, wonderful. So as you all must be knowing, today it's going to be the third session from the GOC part 2, which is what we call as isomerism. Yeah. And in the today's session, what we're going to do is we are going to talk about one really interesting topic, which is what we call as tautomerism, right? Okay. So before starting the session, for the ones who are new to the channel, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here on this NEET Elite channel. Okay. Perfect. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. And do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking right here on this NEET Elite channel, right? So people, you can let me know in the chat box if you guys are super duper excited about these sessions so that we can start directly without wasting a lot of your time. Yes. Good evening, Karthik. Good evening, Priya. Welcome back. Hello, Tesla. Good evening. Thank you, Keshav. Thank you. Well, you can let me know in the chat box if you guys are super duper excited about this session. Yes. Let me know. Give me some green signal from the chat box, right? All right, guys. Wonderful. Perfect, guys. So let's get going. Let's get started with the today's topic, which is what we call as tautomerism. First of all, how do we... People, is the screen clear or there are some reflections coming in? Can you let me know in the chat box first? Is the screen clear? Are there some reflections coming in? Just let me know in the chat box. Is it fine? Okay, perfect. All right, guys, all right. Perfect then. Okay. So what is tautomerism all about? First of all, let me tell you, tautomerism, it arises because of the oscillation of the atom. Tautomerism, it arises due to the oscillation of the atom, which is generally H positive between the two polyvalent atoms in a compound. Okay, so what is this tautomerism all about? First of all, I'm just letting you know about the definition, then I'll make you understand. I'll be telling you its mechanism as well, what this tautomerism is all about, yeah? Just remember the definition first. Tautomerism, it arises because of the oscillation of generally H positive between the two polyvalent atoms in a compound, okay? And due to the oscillation of H positive generally between the two polyvalent atoms, we get two forms. And those two forms are what we call as tautomers, which are always in equilibrium with each other. Few points which I want you guys to remember first of all. The tautomerism, what is it all about? It arises due to the oscillation of atoms, generally H positive between the two polyvalent atoms in a compound. Okay? And due to the oscillation of H positive in general, between the two polyvalent atoms in a compound, it leads to the formation of two different forms, and those forms are what we call as tautomers, which are always in equilibrium with each other. Correct? Okay. So due to the oscillation, we get two forms which are called tautomers, and these tautomers, they are always in equilibrium with each other. Right? Now, how can we understand all this? Okay. First of all, remember tautomerism, it can happen in two systems. Tautomerism, it can happen in two systems. One is called as Diode System and one is called as Triad System. Let's get to know what this tautomerism is all about in Diode System and Triad System. See guys, I have taken a compound right here. Let's assume this is your molecule, right? This is A, this is B, and this A is, for example, attached with one hydrogen, okay? And for example, there's a lone pair on this B over here as well, right? First of all, I'm assuming this A and B as the polyvalent atoms. I'm considering this A and B over here as the polyvalent atoms, correct? What happens in tautomerism? It arises due to the oscillation of atom, generally H positive, between two polyvalent atoms, which leads to the formation of two different forms, and those forms are what we call as tautomers, right? Understand what happens over here. See guys, first of all, if the hydrogen over here leaves as H positive, or I can say something like this, if this A takes this bonded pair of electron towards itself, there will be a negative charge over here on A, correct? And hydrogen leaves as H positive. That H positive is basically attacked by this lone pair on B. So due to which, what do we get? We get one more form. There will be a negative charge on this A, and over here there was a single bond. It will remain as such. Now this hydrogen, it will get attached with B over here. It will get attached with B over here. I'm not showing any sort of charges yet. Okay, just remember, I'm just showing you the phenomenon, right? Okay, so what happened over here is, there in this molecule, what happened? Oscillation of H positive has taken place between two polyvalent atoms in a molecule, right? And whenever you see the oscillation of H positive taking place between two polyvalent atoms in a molecule, this phenomenon is what we call as tautomerism, right? So over here, what did we get? We got two forms due to the oscillation of H positive, right? And these two forms are what we call as tautomers, correct? And people, the oscillation of H positive right here is taking place between two adjacent polyvalent atoms, right? Yes, the oscillation of H positive is taking place between two adjacent polyvalent atoms. So I'll be calling this system first of all as diode system, in which the oscillation of H positive takes place between two adjacent polyvalent atoms, right? And whenever there will be the oscillation of H positive between two polyvalent H positive atoms, two polyvalent atoms in a molecule, it leads to something called as tautomerism. So these two are first of all what I'll be calling as the tautomers of each other. Okay, let me give you one more example so that you understand it properly. See guys, understand properly what I'm saying. Look here. First of all, this carbon over here and this nitrogen, these are two polyvalent atoms, right? And this hydrogen, it's attached with the carbon over here, okay? Now, a possibility can arise. There can be the oscillation of this hydrogen. There can be the oscillation of the H positive between these two polyvalent atoms. And these two polyvalent atoms, they are adjacent to each other, right? So first of all, isn't it a diode system? Absolutely, it's a diode system, right? Now, what is the possibility right here which can happen? See, if hydrogen leaves as H positive, or you can say it like this, if carbon attracts the bonded pair of electron towards itself, there will be a negative charge on this carbon, right? Okay, and this hydrogen leaves as H positive, right? There's a lone pair on this nitrogen. This lone pair of nitrogen can attack this H positive over here, and this H positive will be attached at this position, right? So what you'll be getting over here, you'll be getting carbon with a negative charge, right? And triple bond will be as such, okay? And with this nitrogen, what will be getting attached? This hydrogen will be getting attached right here. Okay? So is there anything missing? Right? There is the positive charge missing on this nitrogen. Correct? So what happened over here? What happened if I ask you? What happened? The oscillation of H positive took place between two polyvalent atoms. First of all, this hydrogen was attached with carbon. Now this same H positive, now the same hydrogen, it's attached with nitrogen. So oscillation of H positive took place between two polyvalent atoms, two adjacent polyvalent atoms. So first of all, it's a diode system. And what has happened? Due to the oscillation of H positive between two polyvalent atoms, right here, what happened? Two forms have got generated. And these forms are what we call as tautomers, which are always in equilibrium with each other. Yeah? As simple as that. You can let me know in the chat box if it is clear to everyone or not. Let me know in the chat box if everything is clear till here or not. This is the example of the diode system. Similarly, there is one more system in which tautomerism arises, right? What is that system called? That's called as Triad System. First of all, you let me know in the chat box if this part is clear or not. Yeah? Let me know in the chat box first. Wonderful. So from now onwards, what we are going to remember is, whenever there will be the oscillation of the atom, which can be generally H positive, between two polyvalent atoms in a molecule, it leads to something called as tautomerism, right? We get two forms, and those forms are in equilibrium with each other. Those are interconvertible, you can say. Yeah? Okay, and those two forms are something which we call as tautomers, right? Okay, moving on. Now people, this is something, from this example you got to know how this tautomerism happens in a diode system. Now let's see how tautomerism takes place in a triad system as well. Okay, I've taken a triad system over here. This is X, single bond Y, double bond Z, right? Let me make it again. See guys, understand properly. This is X. With this X, you have hydrogen attached, single bond Y, and this is double bond Z. This is a triad system over here. This is a triad system over here. Now what is going to happen? Understand. Understand guys, properly understand. Let's say hydrogen over here leaves as H positive, or I can say if X takes this bonded pair of electron towards itself, there will be negative charge on this X, right? Now people, this negative charge on X, can I say negative sigma pi? Can I say negative charge is in conjugation with this pi bond? Due to which this negative charge will come here in the form of bond, and one of the bond will be broken down towards Z, due to which this Z gets a negative charge, and that negative charge on Z is going to attract this H positive which has come out from here, right? That negative charge on Z, that is going to attract this H positive towards itself. So what is the another form which I got over here? I got X, and over here there will be a double bond, right? This is going to be Y. It used to be a double bond over here, but this pi bond has broken down towards Z, so there's a single bond, Z, and Z had a negative charge by means of which it attracted this H positive, so H gets attached over here as well, yeah? Okay, right? So people, what happened over here? What happened over here? Oscillation of H positive took place between X and this Z. Okay, oscillation of H positive took place between this X and this Z, right? First, your hydrogen was attached with X, now the same hydrogen is attached with Z, okay? So oscillation of H positive took place between two polyvalent atoms. So again, we got two forms, and these two forms are what we call as tautomers of each other, correct? I'm sure it's clear to you, right? So these two are basically the tautomers. This is the general example. This is the general example. Now talking about its more precise example, you might have heard about keto-enol form. You might have heard about keto-enol form. Understand? Well, right here I've taken a ketone. Yeah, this is a ketone, correct? Or let me make it over here again so that it'll be properly clear to you. I'm making a ketone. This is CH3, or let me make it as CH2H, like this. Okay, this is CH3, and over here you have got C double bond O. This is one more CH3, correct? People, is it the triad system? Just have a look. This is, for example, X, this is Y double bond Z. X single bond Y double bond Z. So it's a triad system. So tautomerism can happen over here, right? So how it's going to happen? See, first of all, see. This is the double bonded carbon over here. It has formed a double bond, right? So basically this is the sp2 hybridized carbon, right? And all the other sp3 hybridized carbons which will be attached with this sp2, those are called as alpha carbons, right? So this carbon is alpha, this carbon is alpha. So either you are going to take H positive out from here, or you are going to take H positive out from here. Choice is all yours, right? For example, I'm taking H positive out from here, correct? When the H positive will be taken out, when the H positive will be taken out, what is going to happen? There will be a negative charge on this carbon, and this negative charge, right, it's in conjugation with the pi bond, so there will be something like this. There'll be transference of bonds, okay? So there will come a negative charge on this oxygen, and this negative charge on oxygen is going to attract the H positive towards itself. So what is one more form which we'll be getting right here? It's simply going to be, I'll write CH2, and over here it's going to be a double bond. This is C. With this C, oxygen is attached. On this oxygen there was a negative charge, but that negative charge attracted this H positive towards itself, due to which it's going to be OH, and over here you get CH3. Yeah? Okay, so basically what happened over here again? Again, what happened? Again, the oscillation of H positive took place between two polyvalent atoms, right? So again, these two are going to be tautomers of each other. Yeah? And this was the case of the triad system. People, initially you had a keto form. This is a ketone basically, right? From the ketone, what you are getting? See, from the ketone, due to tautomerism, what we are getting? See, this is a double bond. Double bond means E and ene, and this is OH group. OH stands for all, right? So this is something which you call as enol. So ketone got converted into enol. This is called as keto-enol. This is called as keto-enol tautomerism, right? Yeah? And this was the example of the triad system. You can let me know in the chat box if it is clear till here. Yeah? So in short, what you have to do? See, whenever you see a triad system, X single bond Y, double bond Z, break this bond and keep a pi bond right here and take out one of the H and attach with this oxygen over here, right? As simple as that. So finally, you get something as this enol form, right? Right? Let me know in the chat box if it is clear. Let me know fast so that we can move on and talk about a few more interesting things about it. This is just the basics. Latest updates in Valley, you can just drag the video a little back, it'll be a replay for you. Yeah? Perfect. I'm moving on. Should I move on, guys? Just give me some green signal from the chat box. Should I move on? Should I move on? Let me know in the chat box fast. Hi Fazan, good evening. Give me some green signal from the chat box so that I'll move on, yeah? Perfect, guys. Perfect. Tesla, you'll wait. That's something which we call a space tautomerism. I'll be talking about that as well, but at the end. Right? Okay. Let's move on, guys. Let's move on. First of all, in tautomerism, what is happening? Can I say shifting of pi bond is taking place? Right? Remember, bond shifting takes place in tautomerism and it's called as desmotropism as well. This is one more name for the tautomerism, right? Tautomerism is sometimes called as desmotropism as well. Desmotropism, it stands for shifting of bonds, right? Since in case of tautomerism, what happens? Shifting of pi bond takes place. So I can call this tautomerism as desmotropism as well. Remember this over here. Okay? Now people, moving on. Tautomerism is actually an intramolecular acid-base reaction. What it means? Tautomerism actually is an intramolecular acid-base reaction. First of all, what is an acid normally? How do we define an acid? An acid is defined as any substance which donates H positive. Base is any substance which accepts H positive, right? So basically tautomerism, it is actually an intramolecular acid-base reaction. How come? Understand. See guys, this is the keto form over here, right? This is the keto form which I've taken over here. Now what is going to happen in this keto form? What is going to happen? Due to tautomerism, can I say one of the bond between carbon and hydrogen will break and this carbon is going to release H positive as such? So this carbon is donating H positive, it's releasing H positive. So can I say this carbon is acting like the acid? It's donating H positive, I must say. Okay, and that H positive is gained by this oxygen, if you remember. So if this oxygen gains H positive, it's going to act like the base. Correct? So in the same molecule, this carbon is acting like the acid, this oxygen is acting like a base. Isn't it the intramolecular acid-base reaction actually? Right? In the same molecule, one of the atom is losing H positive, another atom is gaining H positive. So one atom is acting like the acid, another atom is acting like the base. So the same thing. The acid-base thing is happening inside the same molecule. So I'll be calling this as intramolecular acid-base reaction over here. Isn't it very simple? Yeah? So remember, your tautomerism is actually an intramolecular acid-base reaction. Okay? One more point. One more important point, guys. Tautomerism contain different, tautomerism contain different functional, tautomers contain different functional groups but are never called as functional isomers. Tautomers, no doubt, they contain the different functional groups, right? For example, see, I'm taking the ketone over here, CH3, this is C double bond O, this is CH3. Now what happens? Due to tautomerism, I'll take one of the H positive out. That H positive I'm going to attach over here, right? So finally you get something as CH2 double bond C, this is OH, correct? And this is CH3. This is what I call as keto form. This is what I call as enol form, correct? One is keto form, one is enol form. Now people, see, over here, this is the functional group. Right here, this is the functional group, correct? So can I say these molecules over here are having two different functional groups? So they must be functional isomers, right? But we do not call them as the functional isomers. Why is that? See, tautomers are interconvertible into each other. They are interconvertible into each other because of the less energy difference, Whereas functional isomers, they are not interconvertible into each other because of the large energy difference between the isomers, okay? Right? So remember from now onwards, Tautomers, these definitely contain different functional groups, but they are not termed as the functional isomers. Why is that? Because functional isomers are not interconvertible into each other because of the more energy difference between the two isomers, right? But in case of tautomers, these are interconvertible, right? These are always in equilibrium with each other. These are interconvertible, right? If these are interconvertible, why these are interconvertible? Because they have got less energy difference, okay? That's why we do not call these tautomers as the functional isomers right here. Okay, so appropriate term for them is tautomers, not the functional isomers, right? Okay. Nadeem, there is the option of repeating, of dragging the video a little back. It'll be a replay for you. Just use your common sense a bit, okay? Right? Just drag the video a little back. It'll be a replay for you. What is the point of repeating? This is a YouTube session. This is not something offline classroom. Okay? I'm sure it's clear to everyone, right? So remember from now onwards, tautomers, definitely they contain the different functional groups, but are not terms as functional isomers. Reason? Functional isomers are not interconvertible, but your tautomers are interconvertible, okay? Tautomers are interconvertible because of the less energy difference between the two, okay? Because of the less energy difference between the two isomers. Whereas functional isomers, they are not interconvertible because of the more energy difference between the two isomers, right? Remember this thing as well. Moving on, the first example of the tautomerism is something which we call as keto-enol tautomerism, which I showed you right now, okay? So still, let's take the example of it, understand. See guys, understand once more the same thing. This is first of all the keto form. Right here you have got the keto group attached, and over here you have got a double bond, and with the double bond you have got OH group attached. So double bond stands for ene and OH stands for ol, so it's going to be the enol form. So how we get enol from the keto form? Yeah, let's check that. This is something which I told you a few minutes back as well. I'm writing this as CH2H, and this is going to be C, this is going to be double bond O, this is going to be CH3, right? Now what is going to happen first of all? See, this is sp2 hybridized carbon. The other carbons which will be attached, the other sp3 hybridized carbons which will be attached to this sp2 hybridized carbon, those are called as alpha carbons. So this is alpha carbon, this is alpha carbon, right? And the hydrogens which are attached with the alpha carbons, those are called as alpha hydrogens. Okay, see what is going to happen over here. Hydrogen is going to leave as H positive. Hydrogen is going to leave as H positive, so that there will be negative charge on this carbon right here. This negative charge is in conjugation with this pi bond. So what is going to happen? This negative charge is going to form a bond over here, and this bond breaks down towards oxygen. Therefore, oxygen gets a negative charge. That negatively charged oxygen attracts this H positive towards itself. So what do I get? I get CH2, double bond, C, single bond, OH, and CH3. So I got the enol form, correct? Right? This is general thing. This is general thing which you are going to remember over here, right? Okay, so keto-enol form. Okay, this is the first example of the tautomerism over here, yeah? Moving on, we have got few other types as well, okay? One important thing, alpha carbon should be sp3 hybridized. What is alpha carbon? That carbon which is attached to the sp2 hybridized carbon. Okay, that's called as alpha carbon. And that alpha carbon should be first of all sp3 hybridized, and it should have at least one alpha hydrogen, then only it can show tautomerism. Okay, remember this thing as well. When tautomerism is possible, when the alpha carbon will be sp3 hybridized, right? When the alpha carbon contains at least one alpha hydrogen, then only this type of tautomerism is possible. Okay, perfect. I'm moving on. I'm talking about the second type of tautomerism. This is called as imines and enamine tautomerism. Okay, imine and enamine tautomerism. What is it all about? Understand. See guys, again a very simple example. See, look here. So first of all, have a look. This compound is what I call as imine, okay? Carbon double bond nitrogen. This is called as imine. Now what happens? Over here carbon is sp2, right? Carbon is sp2, correct? Okay. Now we will understand properly what is going to happen. First of all, this is the alpha carbon, right? This is the alpha carbon over here. The hydrogen attached with this alpha carbon is alpha hydrogen. So it's basically CH2 and one hydrogen. CH2, one hydrogen. So what is going to happen? This hydrogen is going to leave as H positive. When hydrogen leaves as H positive, there will be negative charge on this carbon. This negative charge is going to participate in the resonance, right? Is going to participate in the resonance, and this bond breaks down towards this nitrogen, due to which nitrogen gets a negative charge. And this negative charge nitrogen, what it's going to do, it's going to take this H positive from here. So what do I get? I get CH2, and over here I get a double bond, CH2, double bond CH, CH2 double bond CH, and over here it's going to be a single bond, and NH was already there, one more H positive is going to accept, so it's going to be NH2, correct? So this is one more example of the tautomerism, right? Okay, and this type of tautomerism is called as imine and inamine tautomerism, correct? This type of tautomerism is called as imine and inamine tautomerism, as simple as that, right? Okay. Similarly, let's talk about the third example. It's going to be nitro-si-nitro tautomerism, okay? What it's all about. See, over here, this is the nitro group, NO2 group, right? This is the NO2 group, which we call as nitro group. If you can see, this is X single bond, Y double bond Z. So what is going to happen? Tautomerism is going to happen, right? Well, people, understand. First of all, this is basically CH3, which I can write as CH2 and single bond H. Now, again, what is going to happen? Simple, break this bond in this way, take the H positive over here. As simple as that. I'm not going to show it one by one now. Bond is breaking and this is happening. No. Simple, do one thing. Just break this bond over here. I mean, take this pi bond over here. Take this H positive over here with this oxygen. So what do you get? You get CH2. You get a double bond right here. This is N. This is going to become single bond. And with this oxygen, H is going to get attached. And this coordinate bond is going to remain as such, right? Okay. This is nitro-si-nitro tautomerism. Okay. Correct? Few more examples I'm going to take. Talking about the amides. What is going to happen over here? See, again we have got something else, but over here there is one important thing which you need to remember. See, this is the amide, yeah? Okay. Now this is carbon double bonded oxygen, right? Carbon double bonded oxygen. Either this hydrogen is going to leave as H positive or this is going to leave as H positive. Now which hydrogen will leave as H positive? Okay, which hydrogen will leave as H positive? I'll say that hydrogen will leave fastly. That hydrogen will leave fastly as H positive, which will be connected to more electronegative element. As simple as that. So over here, hydrogen is attached with nitrogen. So I'll say this hydrogen will leave over here as H positive. So what is going to happen? What is going to happen? I'll make it like this. This is NH, for example, NH single bond H, right? Let me make it like this. NH single bond H. So what is going to happen? Just drag this bond over here. Just take this hydrogen over here. What do I get? I get CH3 single bond C. This will be OH. Over here, it's going to be double bond. This is going to be NH right here. See, same thing. CH3 single bond, C single bond OH, correct? And over here a double bond. Right here it's going to be NH, correct? This is one more type of isomerism right here. Yeah, perfect. Let's talk about one more example. That's what we call as nitroso and oxime nitroso and oxime tautomerism, right? Yes. So people, what is going to happen over here? Same thing is going to happen. See, first of all, this is the alpha carbon, right? Let's keep it as CH2 and let's attach one more hydrogen over here. Okay, what you are going to do is just drag this bond right here, just attach this hydrogen with this oxygen, correct? What you will be getting? You will be getting CH2, it was a single bond, now it's going to become a double bond, nitrogen, then single bonded OH, correct? These are basically the isomers of each other, correct? X, single bond Y, double bond Z, correct? They are going to show the tautomerism over here. Similarly, if I take more examples, there is something called as Triasso Tautomerism as well. What happens in this Triasso Tautomerism? Understand. See guys, this is first of all a phenyl ring attached, right? Okay, this is a methyl group over here, right? Now what is going to happen? Understand. This is nitrogen, double bonded nitrogen. Over here you have got a hydrogen, right? I'm going to make this same hydrogen right here, for example, okay? Now, if this hydrogen leaves as H positive, there will be a negative charge on this nitrogen. This negative charge is in conjugation with this pi bond. So what happens? Bond formation and bond breakage takes place, due to which negative charge will come on this carbon. And this H positive, it's going to get attached at this nitrogen at the end, right? So what do you get at the end? This is pH. pH I'm writing as such. Single bond. This is a single bond. With this N negative, H positive gets attached, so it becomes NH, correct? It used to be a double bond, but now it's a single bond, right? This is N as such. There was a single bond right here between two nitrogen atoms over here, but instead of that, you'll be getting a double bond, and with this double bond, with these two nitrogen atoms, over here, methyl group is attached, correct? This type of tautomerism is called as Triasso Tautomerism, correct? This type of tautomerism is called as Triasso Tautomerism. Let me know in the chat box if it is clear. Let me know in the chat box if it is clear. First. Let me know in the chat box if it is clear to everyone. Yeah? Let me know in the chat box first with some thumbs ups. Right? The ones who have not liked the video yet, do like the video. share the video with your friends, and do not forget to subscribe to the channel as well. Yeah. Now people, what we are going to do is we are going to form the tautomers of these different molecules. Okay, understand. So first of all, can you let me know, is the tautomerism possible in the first case? Can you let me know in the first case, is it possible or not? In the first case, tautomerism is not possible. Why is that? In the first case, tautomerism is not possible. See, this is C double bond O, correct? Correct? This is sp2 hybridized carbon. The carbon, this carbon right here, it should be first of all sp3, right? It should be sp3, but it's sp2. Okay, what I told you in the beginning, for tautomerism, there should be the alpha carbon. That alpha carbon should be sp3 hybridized. It should have at least one alpha hydrogen, correct? First of all, is this carbon having any hydrogen over here? This is not having any hydrogen over here. Moreover, it's sp2, right? So tautomerism is not possible in this case. What about the second case? No doubt, see, this is sp2 hybridized carbon and this is sp3. No doubt this is sp3. Your alpha carbon is sp3 right here, right? But is there any hydrogen attached with this alpha carbon? There is no hydrogen attached with this alpha carbon, right? Okay, so there is no alpha hydrogen basically. If there is no alpha hydrogen, so your tautomerism is not going to happen over here as well. Yeah? Right? Very simple. Similarly, if I talk about the third case, in the third case, is the tautomerism happening in the third case? Can you let me know fast in the chat box? See guys, what is going to happen? First of all, just take a look. This is X single bonded Y double bond Z. So it is a triad system first of all. It's a triad system. So what is going to happen? Now I'm not going to break one by one. Okay, just drag this bond over here. Okay, just take this H positive with this oxygen. So your tautomer is going to be CH2. And it's going to be a double bond now. This is C, this is O, this is H, and this is one more H. So these two are tautomers of each other, correct? Which are always in equilibrium with each other, right? Yeah? Perfect? Wonderful. So we will understand. Look here. With this carbon, right here you have got the phenyl ring attached, right? You have got the phenyl ring attached, like this. Right? With this carbon, you have got the phenyl ring attached. Okay, understand. First of all, that carbon which is attached to sp2 hybridized carbon, that's what we call as alpha carbon. So we have, this is alpha carbon, this is alpha carbon, but this is sp2 hybridized, right? This is sp3 hybridized. So from where I'll be taking H positive out? Over here we have got no hydrogen over here. We have got no alpha hydrogen over here, right? Because this carbon is sp2. Okay, but over here you can take the H positive out, and when you take H positive out from here, what you'll be getting, just you are going to drag this bond right here and attach one hydrogen over here with this oxygen. So what you get as the tautomer, it's going to be PH, it's going to be single bond, this is going to be single bond OH, over here it's going to be a double bond, and this is going to be CH2, correct? So these two are tautomers of each other, yeah, which are going to be at equilibrium. We know it because tautomers always remain in equilibrium with each other, correct? Yes. So from keto you got enol, right? From keto you got enol. Similarly, from enol you can get keto as well. Yeah, one the same thing. Let's move on. Let's talk about a few more examples so that you can understand them properly. Okay, these are the products which we have formed till now. Exactly guys, perfectly done. Right, let's take a few more examples. Can you let me know in the first one, is the tautomerism possible in the first one? Can you let me know fast in the chat box? Is the tautomerism possible in the first case? No way. Why? Because this carbon is sp2, this carbon is sp2. No alpha hydrogen at all. If there is no alpha hydrogen, tautomerism is not possible. Yeah? As simple as that. Similarly, if I talk about the second case, understand. Over here you have got the phenyl ring attached. This carbon, number first of the phenyl ring, it is sp2, right? So nothing to do with this. But this is sp3. Over here you have got the hydrogen. Over here you have got the hydrogen. So right here this carbon, this alpha carbon, it has got the alpha hydrogen. Okay, so it can show the tautomerism, correct? So what you are going to do is, see, let's say this is your hydrogen. What you are simply going to do, just take this bond over here, take this H positive over here. What you'll be getting as the product, you'll be getting PH as such, right? It's going to be single bond, this is going to be O, with this O you have got H, and it's going to be a double bond. With this double bond you have got this ring over here like this, yeah? Okay, so these are again what? These are keto-enol form again. This was keto, this is enol, right? Double bond and OH. Double bond stands for en, OH stands for all, yeah? Right? What about the next one? What about the next one? Next one, is this keto or enol? It's already enol. Now I'm going to make it in the form of keto, yeah? Right? So let me know in the chat box what is going to happen over here. Let me know in the chat box first what is going to happen. Let me know first. From enol, you're going to make keto over here, right? From enol, you're going to make keto over here. That's it. That's it, right? That's it. Correct? Correct. Let me know fast. Exactly, guys. You are given with enol right here. From enol, you are going to get the keto over here. As simple as that. Okay? Right? Right. Enol to keto. Exactly. Exactly, guys. You're right. Perfect. What about the last case? Last case is also possible. Have a look. See. This is your carbon double bond oxygen, right? This is sp3 hybridized carbon. This is sp2. So I'm not going to take hydrogen out from here. Correct? So I'm going to take hydrogen out from here, right? There are two hydrogens basically attached. One of the hydrogen I'll take out. Just take this double bond right here, okay? And take this H positive with this oxygen. So with this, finally what you are getting is, you are getting something as, you are keeping the double bond right here at this position, and this hydrogen is going to get attached with the oxygen like this. So this is again your, this was keto, this is enol, right? This again your keto-enol form. Yeah? Right. No, Adnan, that's not important. You can just remember that configuration. That's it. Okay? Let me know in the chat box if everything is clear till here so that I can give you a few more questions. Let me know in the chat box fast. Let me know in the chat box fast. Yeah? Let me know in the chat box fast. Perfect? Wonderful. Let's move on to a few more interesting things. Okay. This is your keto form or enol form. What do you think? What are going to be the isomers of it? What are going to be the tautomers of it? Is this going to show any sort of tautomerism right here? Can you let me know in the chat box fast? Is this going to show any sort of tautomerism right here? Just see, look at it. Is it going to show tautomerism right here? Let me know in the chat box fast. I just want to see. Vijay Lakshmi, I'll be letting you know about that soon. Just wait for it. Is the first one going to show tautomerism or not? Let me know fast in the chat box. Yes. Exactly, guys. Understand. See, this is carbon double bond oxygen. So on one side you have got hydrogens. It is not the alpha hydrogen, right? Okay, this carbon should have been sp3, right? But right now it's sp2, so no tautomerism right here. Yeah? This is important example, guys. This is important example. This is important example right here. See what is going to happen over here. This is carbon double bond oxygen, correct? So this is first of all sp3 hybridized carbon. So I'll be calling this as alpha carbon, and these are the two hydrogens attached with it. So these are alpha hydrogens, okay? So what is going to happen? This is keto. I'm going to make enol, yeah? So what is going to happen over here? Just drag this, keep a double bond in between these two carbons and attach this H positive with this oxygen. So what you'll be getting? You'll be getting something like this. You'll be getting something like this, yeah? Double bond and this is OH. But it does not get formed. Why is that? Over here, understand. From this tautomer, you got this tautomer. But if you look at this tautomer over here, it is not going to get formed. Why is that? Because this molecule is anti-aromatic. Just look. You have got 4 pi electrons. Over here, right? You have got 4 pi electrons. Isn't it anti-aromatic? Anti-aromatic is highly unstable. So it is not going to get formed, right? So tautomerism does not happen in this case. Okay? Right? As simple as that. Now, people, the last case if I talk about, see, This is your carbon double bond oxygen, and this is your sp3 hybridized carbon. So you have got two hydrogens right here attached with this carbon, right? So what you'll be simply doing is, you'll be just breaking this bond or shifting this bond right here and taking this H positive and fix it with this oxygen. So what do I get at the end? I get something like this. This is something like this, right? There will be a double bond. There will be a double bond. And with this oxygen, you get OH right here. These two double bonds will remain as such, okay? This is happening. This is happening. This is happening. This is the aromatic one. This is the aromatic one. This is the aromatic molecule. Why is that? Because it has got 2 pi electrons, right? It's following Huckel's rule. Every carbon is sp2 hybridized. Every carbon is sp2 hybridized, right? It has got complete cyclic conjugation, right? It has got complete cyclic conjugation, and it's following the Huckel's rules as well, 4n plus 2 pi electrons, right? So this is going to get formed. So these are going to be the tautomers of each other, right? I'm sure it's clear to everyone. Yeah? Wonderful. Let's move on then. Let's move on. Let's move on. Let's move on to a few more cases. Let's talk about the mechanism of tautomerism, how it happens, okay? First, you let me know in the chat box if everything is clear till here so that I can move on. Let me know fast, let me know fast. People are saying your video is hanging, is that? Just let me check it from my phone.
I'm sure it's clear to everyone. Yeah? Will be NH2, correct? So this is one more example of the tautomer, right? Okay? And this type of tautomerism is called as imine and in.
It's fine, guys. It's fine, it's fine. Okay, let's move on then. Hi, Bharat, what's up? Okay, talking about the mechanism of tautomerism, let me tell you first of all, this tautomerism, it can happen in acidic medium, it can happen in basic medium, it can happen in neutral and gaseous medium as well, okay? Remember, tautomerism, it can happen in acidic medium, basic medium, as well as your neutral or gaseous medium as well. Now we are going to see the mechanism of tautomerism in acidic medium first, then in basic medium, and then at the end in neutral medium, okay? Let's move on. In acidic medium, what happens? Understand properly what happens in acidic medium. See guys, over here I have taken the keto form. This is the keto form. CH3, this is C, this is double bond O. This oxygen has got 2 lone pairs, right? This is CH2 and this is CH3. Correct? Okay, in acidic medium, that means I have got some acidified water, H positive in presence of H2O. Correct? What is going to happen? First of all, this lone pair, it is going to attack at this H positive, okay? When the lone pair attacks at this H positive, what you are going to get? You are going to get something like this CH3, this is C, and it used to be double bond O, now it's going to be double bond OH positive when it gets attached, right? When this H positive gets attached. Rest everything is same. Rest everything is same. CH2, this is CH3 over here, correct? Now people, after this, what is going to happen? Understand what is going to happen. See, this positive charge is basically on oxygen, and positive charge on more electronegative element makes it more electronegative, right? Positive charge on an electronegative element makes it more electronegative. So this pi bond is going to break towards this oxygen, right? Due to which, what is going to happen? I'm going to make a resonating form, yeah? Due to which, I'll say carbocation gets generated when this bond gets broken down towards oxygen. So there will be a positive charge on this carbon right here. This is CH2 as such, this is CH3, and over here you get OH. Correct? Right? Now people, in water, what is going to happen? In water, what is going to happen? This water is going to take H positive out from either this alpha carbon or from this alpha carbon, right? See, this is basically your a carbocation over here, right? Positive charge on this carbon. The carbon which will be attached with this carbon, those carbons which are going to be attached with this carbon, those are called as alpha carbons. So this one and this one, these are alpha carbons. So these 3 are alpha hydrogens, these 3 are alpha hydrogens, correct? So if this water takes H positive out from this CH3 over here, what is going to happen? When the H positive, this water is going to take out, there will be a negative charge on this carbon, and that negative and positive will make a bond over here. So 2 kinds of possibilities arise. Either there will be a double bond right here between these two carbons, or there will be a double bond between these 2 carbons, right? I'm going to show you the both possibilities, right? So I'm assuming this water is going to take H positive out from here. So what you'll be getting, when this water is taking H positive out from here, there'll be a negative charge on this carbon. So there'll be a double bond between these two carbon atoms. So it's going to be CH2 and over here double bond, right? It's going to be C as such, and with this you get OH over here like this, and then you write CH2, then you write CH3. This is one possibility. What is the second possibility over here? This water would have taken H positive out from this carbon as well, and when this water takes H positive out from this carbon, there would have been negative charge on this carbon, right? And this positive negative would have formed a pi bond. So at that time, what would have been the possibility? This CH3 would have remained as such. This is single bond oxygen with this single bonded carbon, and over here OH. Over here there would have been a double bond. This is going to be your CH at that time, and this CH is attached with CH3, right? Okay. Now people, if I ask you, which one is going to be the major product over here? Which one is going to be the major product? See, this is a double bond, okay? This is alpha carbon, this is alpha carbon. So these three are alpha hydrogens, these three are alpha hydrogens. This double bond is stabilized by 6 alpha hydrogens, right? Look at this double bond. This double bond is stabilized only by these 2 alpha hydrogens, okay? So if this double bond is stabilized by maximum alpha hydrogens, so this one is going to be the major product. So you got to know this one is going to be the major product, this one is going to be the minor product over here, right? This is the mechanism of tautomerism in acidic medium, yeah? Right? Let me know in the chat box fast. Let me know in the chat box fast. Let me know fast in the chat box if it is clear to everyone, yeah? Ikra, just drag the video back, it'll be a replay for you. Okay? Still, I'm going to give you one more example. With that example, everything will get clear to you. See guys, same thing. One by one we have done. See, first of all, this lone pair is going to attack this H positive, so that it's going to be OH positive right here. Positive charge on electronegative element makes it more electronegative. So double bond breaks in this way, okay, so that carbocation gets formed right here, okay, carbocation gets formed. And in presence of water, this is a rate determining step. I forgot to tell you that. This is the rate determining step now. Okay, now water is either going to take this H positive out or this H positive out. If water takes H positive out from here, there'll be a double bond between these two carbon atoms. If water takes H positive out from this carbon, there will be a double bond between these two carbons. So two possibilities arise. One is going to be the major product, one is going to be the minor product, right? When the what did I say? Just a second. Yeah, exactly. One is going to be the major product, one is going to be the minor product. Yeah. Why this one is the major product? Because this double bond is stabilized by maximum alpha hydrogens, 6 alpha hydrogens, and this double bond it's stabilized only by 2 alpha hydrogens over here. Yeah. Okay. Let's take a few more examples. Yeah, Karthi, you can see that. You can see that. Okay, this is one more example. We are supposed to write the major and minor enol forms. We are supposed to write the major and the minor enol forms with the mechanism, okay? So first of all, this is the molecule which is given to me. The same thing, it is in the acidic medium. Now this lone pair is first of all going to attack at this H positive. So what do you get over here? You get something as O, and this is going to be OH positive. It's going to be OH positive, and then rest is same. Rest is going to be same, and over here you've got a methyl group attached, right? Now, positive charge on electronegative element makes it more electronegative, so this bond breaks in this way, yeah? So what happens? You get a single bond like this. You get a single bond, and this is going to be basically OH, and carbocation got generated right here, and this is your methyl, right? Now people see, this carbon is sp2, and these two carbons which are attached to sp2 hybridized carbons, these are your alpha carbons. So this is my alpha carbon, this is my alpha carbon as well, okay? Right? So either you are going to take H positive from here, or you are going to take H positive from here. If you are taking H positive from here, there will be a double bond right here. If you are taking H positive from here, there will be a double bond right here. So two possibilities arise. In water, what is going to happen? This is your rate determining step first of all. What is going to happen? Two kinds of products will get formed. See guys, understand. This is OH as such. If I'm taking H positive out from here, there will be a negative charge on this carbon. Negative positive is going to form a bond like this, right? And rest, everything is same. Yeah, this is one product. Similarly, one more product. This water, if it takes this H positive out from here, what is going to happen? If H positive leaves from here, there'll be a negative charge on this carbon. Negative positive makes a bond over here. So what is my another product is going to be like this. There'll be a double bond right here. This is OH and this is methyl as such. Now, if I ask you which one is going to be more stable among the two? See, this double bond, it is stabilized by maximum alpha hydrogens. See, first of all, if I note down, this is the alpha carbon, right? This is the alpha carbon, right? This is the alpha carbon, okay? Those carbons, those sp3 hybridized carbons which are attached to sp2 hybridized carbons are called alpha carbons. So this is alpha, it is attached with sp2 hybridized carbon. This is also attached with sp2, this is also attached with sp2, right? All these three are alpha carbons, right? With this alpha carbon, you have got 3 hydrogens attached. With this, you have got 2 hydrogens attached. With this, you have got 2 more hydrogens attached. So 3 plus 2, 5, 5 plus 2, 7. So you have got 7 alpha hydrogens, right? I mean, this double bond is stabilized by 7 alpha hydrogens. What about this double bond? This is the alpha carbon, right? And this is the alpha carbon, correct? Okay, so you have 2 alpha hydrogens right here, 1 alpha hydrogen right here. So this double bond is stabilized by 3 alpha hydrogens, right? This double bond is stabilized by 7 alpha hydrogens. This is stabilized by 3 alpha hydrogens. So this is definitely going to be the major product, right? The one stabilized by maximum alpha hydrogens is going to be the major product, right? Let me know in the chat box if it is clear to you. Let me know in the chat box fast. Let me know in the chat box if it is clear to everyone fast, so that I can move on. Yeah? Let me know in the chat box fast. Let me know in the chat box. Perfecto, guys. Yeah, there is some lag. I don't know why. But anyways, it's fine. All right, let's move on. Let's move on. And this is something which I told you, yeah? This is something which I told you. So you get 2 products right here. One is going to be the major product, one is going to be the minor product, right? Why this is the major product? Because this double bond, it's stabilized by maximum alpha hydrogens, right? Over here, you don't have a lot of alpha hydrogens.